So, hello everyone. My name is Akihiko Yamaguchi. Uh, Thank you. So, today I will talk about vision-based tactile sensor FingerVision, and today I will talk about this topic from open source hardware and software view, and also I will talk about the commercialization about FingerVision. So this is about my brief background. I got a PhD in Nara Institute of Science and Technology in Japan and worked for 4 years there. And during that time, I was working on robot learning like this, the reinforcement learning for some sort of small robots. And then I moved to Carnegie Mellon University, and I studied the robot learning about robotic manipulation, especially about deformable objects. So I studied the manipulation of a liquid. I implemented a robot to manipulate objects for the water or other types of liquid. And then I tried to do some other types of manipulation, like, for example, grasping food items or cutting or peeling banana and so on. And during that time, I felt the necessity of a tactile sensor. And so I started to develop a tactile sensor named FingerVision. That is a vision-based tactile sensor. And so this is almost the initial version of tactile, the FingerVision. And recently, I'm also working on developing more but the degrees of freedom robotic hand like this, and it has a whole surface FingerVision sensor. And so today I will talk about this FingerVision sensor, and it has a history like this. I started to develop a FingerVision sensor in 2016. And then I made it open source. And recently I commercialized this FingerVision sensor. So I established a company named the FingerVision Corporation in last year. So today's main focus is about the open sourceness of this FingerVision, because this workshop focuses on that. So this slide is showing my expectation about the open sourcing of the FingerVision. So what do we expect for an open source about the FingerVision? So I think those are almost a common motivation to people to make their software or hardware to make to open source. So one is increasing the developer resource. So we can expect encouraging external engineers to join the development of software or hardware. And the increasing the transparency will be also beneficial to engineers, because the engineers want to know the inside the details about the software or hardware that they are using. And it's also important to avoid reinvent of wheel. And increasing the awareness is it's also an expectation. But the most important thing that I wanted to make with open sourcing the FingerVision is popularization of the technology. So what I expected is anyone can. I want to create a state where anyone can use the technology, the software or hardware. And the software, the FingerVision is used everywhere. And by doing that, I wanted to solve some technical issues in the society. So today I will go in order to go deep about go details about FingerVision. I will start with some general story about tactile sensors. So there are some typical tactile sensors for robot hand. Probably most common approach would be capacitive-based or resistance-based tactile sensors. And there are some other approaches. One is barometric-based or magnetic-based. And the vision-based is also one of probably a famous approach to create tactile sensors. And the FingerVision is this kind, in this kind. So one motivation that I'm creating a FingerVision is automation of this kind of factories or situations. So for example, in food factories, some processes are still done by human beings. And the example is food factory. And because the food items are, I think it's more difficult to handle with a robot, because compared to some industrial parts like screws or rigid items, the food items has different deformable shapes, and each of them do not have the same or consistent shape or the hardness or some physical properties. And so the question here is, can we use the existing tactile sensor in automation of such processes? Because tactile sensing is, I think it's an important component to automate processes in such a scenario. Because each food item has different shapes or different physical properties, then the robot needs to adapt to those items. And doing that only with a vision is a bit difficult. So I think the tactile sensing is necessary for this kind of situation. And the question is, can we use an existing tactile sensor for using this kind of scenario? And probably this is there are many issues or difficulties. And so that's why if we see the industrial robots, most of them do not use tactile sensors. And there are some different issues, various issues in tactile sensors, and they make installation to industrial robots difficult. So one difficulty is the fabrication or installation to a robot hand. We need to install a tactile sensor into some very small robot hand. And wiring is also an issue. And the second one is the durability, because in an industrial situation, the robot needs to repeatedly do pick and place or other types of tasks. And so physical or chemical or probably thermal durability is required to tactile sensors. And performance and programming is also some issues that we need to solve. And so this slide illustration is showing the vision-based tactile sensor. So left one is the typical structure of vision, and then the right one is the typical tactile sensor. And the vision-based tactile sensor can be illustrated like this. So we introduce an interaction layer in order to visualize physical phenomenon. So when external force is applied to this interaction layer, it is visualized, and then this phenomenon can be captured by the vision sensor. And there are many approaches of vision-based tactile sensor. So we have some different selection of for vision. For example, photodiode or proximity sensor, or we can also use a usual RGB camera, or we can use a depth camera. And about the design of our interaction layer, we have some different ways. And based on the sensing principle of to design the vision-based tactile sensors. And then there are the examples of vision-based tactile sensors. As far as I know, this is the initial version of vision-based tactile sensor published in 1988. And probably the most famous vision-based tactile sensor is GRSI from MIT. And FingerVision is also one of this kind of version. And the one feature that is different from other tactile sensor is the transparency of the skin. So all other tactile sensors have an opaque skin on the surface. That's in order to make avoid the reduce the effect from external environment. That makes the computer vision easier. But the finger vision made it completely transparent. And from that, we have some benefits about the increase of the modality of tactile sensor. So this is the prototype of finger vision. It has an elastic skin and camera and some markers are placed on the surface of the elastic skin. So this is the interaction layer that I mentioned before. And when external force is applied to this elastic skin, the skin deforms and the camera can capture the deformation of the skin because we can see the marker movement from the camera. And from that information, we can estimate external force. And we can also get slip information from this camera information by analyzing the previous frame and current frame to get the slip information. So and because the skin is completely transparent, we can see directly the target item. And so we can get the texture or, for example, orientation of the target item from this camera by analyzing the camera information. So that's why this sensor is a multimodal. On the other side, the structure is very much simpler. We just need a passive component, the elastic skin with some hard layer. And the camera is not much expensive. It's kind of a low cost, and the structure is also simple. So the fabrication of this sensor is also not expensive. And other important feature is it's physically robust because the skin that interact with the external force is a passive component, and so even if it is damaged, replacing that component is not much expensive, and because it's just a passive component, so it has some physical durability. And so this is a summary of the advantage of finger vision. Because we have established wiring technology for cameras, so it is much easier to install to a road hand. Also, the size is a bit problematic. We need to consider carefully about the size, but rather than that, the other disadvantages of vision-based the disadvantages of tactile sensors are almost clear. And regarding the durability, as I mentioned, it's durable compared to existing tactile sensors. And in particular to finger vision, we are using a silicone skin, and it has good durability regarding the chemical and the thermal. And about the performance, the vision-based tactile sensor typically has a higher resolution. The only concern is the frame rate. So it depends on the frame rate of a camera, and the one that we are using is 60 FPS. It's not much low, but not much high. And other important feature of finger vision is the customization of the surface. So because it's we don't have large constraint restriction about the interaction layer, so we can design flexibly about the shape of interaction layer. And so this is the collaborative work with Kanazawa University and myself. They are developing the special robot skin. It can change the friction coefficient according to the external load. So when external load is low, then friction coefficient is low. And it is good for example, slipping on the target surface or stroking target surface. And when the external force is higher, the friction coefficient becomes larger, and it is good for stably grasping object. And they call this structure as covers CVS, which means contact area various skin. And this is good for manipulation. And we integrated, unified this skin with FingerVision, and by making this structure with transparent skin and installing the camera underneath. So we made the FingerVision with this kind of surface structure. And this was possible because we can flexibly modify the surface of the tactile sensor. And this is a bit detail about the force estimation of FingerVision. So as I mentioned, the force is estimated by tracking the marker movement. And so that was done by comparing the initial marker movement and the current marker movement. Both of them were captured by the camera. And the shared force, the horizontal force is estimated from the horizontal movement of the markers. And regarding the normal force, or vertical force is estimated from the marker size change. So because the horizontal marker movement is more sensitive than the marker size change, so the sensitivity of the normal force, the horizontal force, is much better than the sensitivity of normal force. So in order to increase the sensitivity of a normal force, I modified the marker shape. So originally, the marker is embedded inside the elastic layer surface, but I created the whisker structure on the surface of the sensor skin. And so when there is an external force, with a small external force, the whiskers can deform. And because the skin is completely transparent, so camera can see the whole shape of the whiskers. So it can sense the small movement of the whiskers, and it increased the sensitivity of the sensor, about the normal force sensitivity. And this is a bit detail about the slip detection. So in the FingerVision, so there are several types of slip detection with tactile sensors. So one approach is a direct measurement of tactile sensor, the slip, and the other is the indirect measurement of a slip. So in an indirect approach, the slip information is estimated from the force estimation. And on the other side, the FingerVision can estimate and detect the slip directly from camera, the video analysis. So because the FingerVision has a transparent skin, and it is looking the target object, the contacting object, and so we can get we can compare the previous frame and the current frame, and then applying the simple computer vision technology like optical flow or background subtraction, we can get the difference. And if there is a difference, we can say there is a slip. And so this is a kind of a direct approach, and it has a beneficial that we don't need the estimation of a force. So for example, when we are manipulating a very lightweight object like a paper craft or origami, we cannot expect the force detection about manipulating those objects, but FingerVision can detect the slippage even if the target object is very lightweight. And so the slip sensitivity is very high with the FingerVision sensor, and that's one important feature. And some other modalities shown here. One is the thermal estimation by introducing an infrared camera, and the other is the orientation estimation from the directly analyzing the camera information. And this one is a bit funny because we are directly using the camera analysis to estimate the readings level on a food item. And so this is an example of manipulation with FingerVision. So because as I mentioned, it has sensitive, very much sensitive slip detection. The robot is using the feedback of using the slip detection. So control scheme is very simple. If there is a slip, the gripper increases the force, grasping force. And repeating that until there is no slip, the robot can adapt the grasp to the target object. And this approach is very strong. We can apply this to various objects, including origami for grasping. And we can also grasp some heavier objects like food items, broccoli, and it can also apply to some complicated shape of objects like oyster mushroom or some rubber toy. And it can be applied to some, for example, raw egg or potato chips or something like that. And this is also another example in grasping grape and green onion. And this is another example of using the FingerVision in robot manipulation scenario. So here the task is pivoting, rotating a target object in hand without placing the target object. So the FingerVision here is used in two ways. One is estimating the orientation of the grasped object, and the other is detection of a slip. In this case, the robot creates the slip on purpose and then moves the grasped object to target the orientation. And here we also introduced the curves structure that I mentioned before. And by using this, we can very slowly control the grasped item. And so the accuracy of the error of from the target orientation is less than 1 degree. So I think it's a good accuracy. And this is another example of using the FingerVision in manipulation. So it is using the slip-based grasp adaptation. And then during that, it also estimates the label information. There are two types of labels in the food items, and it is sorting based on the estimation of the labels. And so this is other updates about FingerVision. Some types of manipulation other than grasping, we need more degrees of freedom to the robot hand. And the challenge here is installing the FingerVision to all robot links. So I miniaturized the FingerVision sensor and installed onto this. This is 4 degrees of freedom robot hand, and so this is an example of FingerVision information sensed from all cameras. So it has 5 rings, and it has 5 FingerVision sensors. And showing the FingerVision sensor, showing a target icon here, it can sense from all views. And this is also a test of grasping with target item using the slip-based control. The question here is how to map the slip information sensed from each link to robot at the actuators. And I'm still working on how to make a better controller to control the gripper here. And I will present it in some future conference. And yeah, so let's do the conference, the workshop main topic about open sourcing and commercialization. So in 2017, I made the FingerVision project open source, and I made a GitHub page and website. It includes the hardware design, such as CAD file and fabrication procedure. And I also opened published the software to process the FingerVision data, as well as some controller program using the robot gripper. And yeah, of course, I published some publications and made some mailing list. So it is still active, and so if you visit this website, you can see the all contents about this. And I also do some hackathon using the FingerVision and some small toy robots, and gathering the people and making some applications with a FingerVision enabled robot. And so after some years, I found that there are some succeeding research items using the FingerVision. So for example, this is from China, and they made a custom version of FingerVision. And this is made in University of Washington. They implemented this to the robot hand of jack arm, and they used it for the feeding project of grasping some food items to people in a robot assistive robot context. And this is from the university in Germany in a context of machine learning or robot learning. And so I think it's somehow successful about the open sourcing the FingerVision, because other researchers made a succeeding version of FingerVision. But I also felt that it is there is also a hurdle or difficulty to make a state where FingerVision sensors are more widely used in practical situations. So, for example, automation in a food factory or something like that. So I think there is a missing component. We need a player to implement the FingerVision sensor into a system, like a system in a food factory or automation. So the reason so let's think about the food, or what kind of players are making the automation in a food factory. So in making automation of a food factory, various kinds of players are included. So for example, robot makers, of course, and gripper makers, tactile sensor makers, or other sensor or hardware makers, system integrators, and the important player being system integrators. They will combine the components to solve practical some target tasks, like for example, the packaging, pick and place to package the bento box or lunch box. And so they unify the entire food factory system. And so because the existing robotic system integrators do not have knowledge or technology about using the tactile sensor. And so I think it's very much important component, and we need to. So that's why we established a company to do it by myself. So this is a member of the FingerVision company, and our challenge is we of course make the tactile sensor products, but we also do some system integration. For example, the automation of food factory by making a robot system for that. And so this is an example of the target factory that we want to automate. There are so many human labors here, and they are doing pick and place of food items. And this is an example of the product that we are making. So it has a finger vision sensor installed in the robot hand and doing a pick and place. But we also made some peripheral systems for make this robot work. All right, so it's the last phase. Our company is hiring people, engineers. If you are interested, please join us. All right, thank you so much.
Yeah, thank you for the talk. Unfortunately, in the interest of time, I think we have to move on to the next talk. If you have any questions, I'm sure he will be around. So please ask him online. Yeah, thank you.
All right, thank you.